Okay, I just wanted to make a quick video to clean up and make crystal clear what to do in these specific heat problems where things are warming and melting and so on and so forth. Our strategy is, regardless of whether things are heating up or cooling down, to write all the heats on one side of the equation. So it's going to look something like this. In other words, we'll add them all up on one side and set them equal to 0. Don't try and equate things to each other. Add things, set them all equal to 0. Remember, heat is a conserved quantity. Heat is conserved, and what that means is that if you've got a bunch of heats added to your system, they all have to cancel each other out. That's what conservation is. Okay, so if we write this down, in this case, I have aluminum, I've got ice, and then later in the problem, it says something about melted water. So I probably have water too. I am adding the heat in all three cases. Okay, now the heat may turn out to be positive or negative, and we'll kind of deal with that as we go. But the big idea here is that if the heat for a particular substance is positive, that substance is gaining heat. So I've got it here. It says if Qx is positive, then X has gained energy. In other words, if Q aluminum was positive, aluminum would gain energy. In this case, aluminum starts at 140 degrees, so we can be pretty sure that aluminum is going to lose energy. So we expect that to be negative rather than positive. So let's write this out a little bit more specifically. So for the heat that the aluminum loses, that's just temperature change. So that's MC delta T. Then we've got to deal with the latent heat of ice. So there's that L guy in there. Remember, there's a phase transformation that happens here, and the temperature doesn't change at all. So here you've got MLF. And then once the ice melts, it's water. And then here you've got temperature change again. Okay. Now, to deal with the temperature parts, the temperatures will take care of themselves. The temperatures, this will tell you whether things are positive or negative. There's nothing additional you need to add. With the latent heat, though, we do need to look up the value of the latent heat. And if you look up the latent heat of fusion, because this is ice to water, you'll find it's 333 joules per gram. You have to be a little careful here, though, because latent heat of fusion means ice turning into water, but it also means water turning into ice. Now, when ice melts, you need to give it energy. You need to put energy into the ice in order to melt it. So based on this definition, that would mean that Q is positive. But based on the way I've written it, it's already positive. I have 333 joules. On the other hand, if ice were to freeze, as the ice freezes, it actually gives off energy. So the way I like to think of it is you always write plus MLF, but to freeze, the latent heat of fusion is negative 333 joules per gram. In other words, it's going to give up energy, lose energy, rather than gain it when it freezes. Okay, so that's the big thing in this problem, and that's how I recommend keeping track of the signs. The rest of this is plug and chug, but just to show you what it looks like when you put the numbers in. You've got 200 grams of aluminum. The specific heat of aluminum is about 0.9. The initial temperature of the aluminum was 140. I put a TF here. The final temperature of everything will, of course, be the same. That's why I don't put a subscript on it. Okay, I got 25 grams of ice. This is how much each gram of ice takes to melt. And so I've got 25 grams. That's why you multiply them together. And then this is the amount of energy it takes to heat up that 25 grams once it's turned into water. If I sort of grind through the math, you'll end up with a temperature of about 60 degrees. That's not really the important part of this problem. Really, what I want you to take away from this is this. If Q is positive, then whatever heat you're talking about, that's gained energy. And I want you to take away this as a technique. I promise that writing everything on one side and equating to 0 is not just going to be useful for this category of problems, but all sorts of other problems that you'll encounter in physics. It's often much easier to set it up this way than it is to try and balance things on either side of the equation. Okay, hopefully this has been more helpful than confusing.